Okay, so this video is focusing on Young's modulus and what it is and how we calculate it. So I'll put Young's modulus, oh, spelled that wrong already. Young's modulus there. So we already know that stress and strain are related. We know that stress is the force per unit area. So if you remember that stress is a sigma, is the force per unit area. And we know that strain is how much something lengthens or deforms due to its stress. So we know that strain is the extension over the original length, or not delta, just length. There we go. Okay, so depending on a material, we know that all materials are going to deform differently depending on what's happening to them. And if you apply a force, that material will deform in some way. But different materials require different forces and will deform differently. So the way we look at that is something called Young's modulus. So Young's modulus is defined by a symbol. Well, we'll go for symbols first. Young's modulus is an E. So we give it the symbol E, like so, not a curly E, just a normal E. And that is a ratio between your stress and your strain. So it's a ratio between your stress and your strain. Stress and strain, and it is constant for the material that it is the number of. So for any given material, they will all have their own value of Young's modulus, and that will remain constant as long as your limit of proportionality isn't exceeded. So I'll put per material, I'll put constant as long as, I'll put LOP, limit of proportionality, not exceeded. So each material should have its own Young's modulus. And Young's modulus, as we said, is a ratio between stress and strain. So if we were to write that in an equation, you're going to have E, which is your Young's modulus, is stress, sigma, over strain, epsilon, like so. So it is simply a ratio between the two, and it should be constant for any material. Now, if we're going to look at units, remember that stress has the unit of newtons per meters squared, like so, or pascals. And we know that strain has no unit. So this was from the previous video. So if we're looking at these, we can now see that the only unit we have available is your sigma up here, like so. So that is actually the same unit for Young's modulus. So Young's modulus is also measured in either Newton meters squared or pascals. So they can be either. So we can also say that 1 pascal is the same as 1 newtons meters squared. So it is exactly the same, Newton per meter squared rather. So we're happy that our Young's modulus value is constant, and it depends on the stress and strain. So of course we're going to look at a graph. So if we do a stress strain graph, like so, stress strain, so we know that stress goes on the y because I said it first. So stress strain graph, like so, and these graphs will usually be a straight line initially, and then they'll reach their limit of proportionality, and depending on the material it will go like so. You might have sort of ones like that, so they should be straight initially. And obviously with graphs we always like to look at the gradient. So if we were to say the gradient equals delta y over delta x, looking at your graph, you know that delta y is going to be the change in stress and delta x is going to be your change in strain. That looks very familiar. We know that that is the same as Young's modulus, so we can say that the gradient of a stress-strain graph, so gradient of stress-strain graph, is exactly the same as the Young's modulus. Like so. So those are your basics of Young's modulus. It's all about relating stress and strain, and your units are exactly the same as stress.